I am updating the homework. I added a few more questions last night. It'll be, like as usual, finalized by 5 o'clock today. Once 5 o'clock today goes by, then that's the final assignment. And we'll turn that in Wednesday. Any questions? So what did we do on, can't remember what we did on Friday. Surface area and volume? Took the quiz. What's that? Oh, we did acceleration, right. Okay. So yeah, so we did acceleration, velocities, and displacement. And then today we're going to talk about work. Did you know you hadn't done any work yet in this class? Get it? Hey. They don't pay me for jokes. All right. So work is a quantity in physics. It's a force applied over a distance. And that's quantified as force times distance. So to get the amount of work, so if I push this table 3 meters, if I'm pushing on it with 30 newtons of force, then that I've done some amount of work. Okay? The force that I exerted times the distance that I moved it is how much work I did. Okay? So as we look at this quantity of work, it's going to be no different than, so I'll talk about that at the end of the slide. All right, so the units are Newton meters, right? Force times distance. The force in metric units is newtons. Distance is meters. So Newton meters. All right, and so here's an illustration. You may have seen this before. This is the school of the Midvale School of the Gifted. Okay? And so, is he doing any work? Is he doing any work? He's sure putting in a lot of effort, right? He's putting in a lot of effort to try to get through that door. But because there's no distance involved, it doesn't matter how much force he pushes with, there's no work being accomplished. So when more accurate to talk about work is, in quantifying it, is what is actually accomplished. And nothing's being accomplished here by this gifted student, okay? All right? It's because there's no distance, right? So it's force times distance, okay? So accomplished work is really a more fitting description for what we're quantifying. How much gets done, right? How much, so your distance times the force exerted. So just like all the other quantities that we've been working with, what volume, arc length, area, acceleration, velocity, displacement, it's going to be the same pattern as before. We're going to focus on the quantities involved, and so now there's 7 new quantity, work. And so how will we find the accomplished work or the accumulated amount of work? What are we going to need? The rate of change of work, right? The rate of change of work. So if we have the rate of change of work, and with the rate of change of work, we can accumulate little bits of work, right? Little bits of work, and then we can accumulate those just the same way we've been accumulating volume, arc length, area, etc. Okay, so where's the complications here? Force, the force could vary across the distance, right? So say as I'm pushing that table, maybe I start with lots of force, but then it's getting harder, so my ability to apply that force gets less and less. And so my force decreases as I'm pushing, maybe, possibly. Or the distance, we're not just talking about a straight line distance, right? So it could vary in a strange way. So that's what complicates this and forces us to look at what? Little bits of work at a time, right? Little bits of work at a time. It's not just 30 newtons times 3 meters, right? So yes, if the force was constant and the distance was a straight line, then it's an easy calculation, force times distance. But with these complications, we have to do what we've been doing all along in this course, is look at little bits of work, right? Get our rate, our changing rate, and think about the work being accomplished in little bits, and we're accumulating all those little bits. Okay, so let's talk about an ant here. So I have an ant. and he's pushy because he's pushing a seed along this path. The ant pushes with a constant force of 0.03 newtons. How much work will the ant have accomplished at each distance along the path? So what we're looking for is a work function. And that work function is going to tell us when the ant is to a certain point, how much work has he accomplished so far. So then we could pick any point along the path, and it would tell us, the function would tell us how much work has been accomplished so far. Okay? So we know that work is, our general formula is work equals force times distance. So what's complicating things here? The force or the distance? Yeah, the distance is this is a weird path, right? The force is easy because it's constant force, okay? So it's a constant force. So then we're going to have to talk about little bits of work, right? So instead of just one calculation or just setting up a formula quickly, we have to talk about little bits of work. And so little bits of work, how would we think about quantifying a little bit of work? What would a little bit of work be in this case? So if work is force times distance, then a little bit of work is also force times distance. What is our force? All right, that doesn't change, so we can just use 0.03. So then any little bit of work along the way is going to be that constant force times a little bit of distance, right? A little bit of distance. And how would what would a little bit of distance be here? Along this weird, complicated curve. What would, using the symbols that we've talked about so far, a little bit of distance would be what? D, what do we call it? S, little s. Remember, arc length. Arc length, right? It's not going to be x or y. X is just a little change in horizontal. dy would be a little change in vertical. We need a little change in the arc length, and that's our lowercase s, right? Lowercase s is our arc length, and so ds. Okay, but so if we had that function as a function of x, so the path of the ant is f of x equals x plus 0.3 cosine of 7 times sine of 3x. And I want to get my rate of change of work, right? We want to get rate of change of work in terms of x. In terms of x. So I've got a little bit of work here, but I need to figure out what my rate of change is. In other words, the rate of change is going to be something times what? dx. Sorry, the little bit of work. The little bit of work that I have will be something times dx, and then that something will be the rate of change, right? The rate of change. So I wrote that in the wrong place. So if I can write that 0.03, the force times a little change, as something times dx, we know that something then is my rate of change of work with respect to x. Right? So how do I write this? 0.03 times ds. I want to write that as something times dx, and I want you to collaborate with people around you and see what you come up with as I start attendance. How can I write 0.03 ds as something times dx? You have the tools to do that. You just got to remember, okay? What'd you guys come up with? So how are we going to get this 0.03 ds as something times dx? Okay, so what is the square root of something something? When you say that, you're talking about what part of this? ds. So we're still going to have the 0.03, right? So we'll have the 0.03. And then you said square root of 1 plus derivative of so this is a little bit of arc length of what? A little bit of arc length of what? Function f, right? And so our arc length ds says 1 plus derivative of f. Just the derivative of f squared. And then also with the ds is dx, right? So this whole thing is our ds. Did you come up with that, others of you? Yeah. Doesn't make sense. Okay, so then what is our rate of change of work in this case? What's the rate of change of work? Yeah, please. Yeah, it's the same thing, right? The derivative of, we have different notations, right? We have f prime. We have we write df dx. We write r sub f of x. Those are all the same thing. They're all the rate of change of the f function. Yep, those are all representing the exact same thing. Okay, so what is our rate of change? Was there another question? What's our rate of change then? 0.03 times the square root of 1 plus, I'm going to write f prime, so it's faster, dx? No, because this is, right, this is like our dy equals m dx, right? dy equals m dx, so this whole thing is the m, right? This whole thing, this is our rate of change. This is our rate of change of work with respect to x now. Okay, so now how can we make this? Now we want to write the work function. We want to write the work that the ant has done, starting from 0 to x. So work on that for a minute. So write out, what would you write out so that we'll get, for any value of x, we have the current amount total accomplished work of the ant. Go. The work function? Integral? Zero to x. Uh-huh. He's asking, is it right? Yeah, good job. See, by writing the rate of function, we've done all the heavy lifting, right? So everything, all the hard part is over if we just remember our basic net accumulation function, right? So our net accumulation, no matter what quantity we're talking about, we just need that rate of change, and we know we can write the net accumulation. Okay? And so then if we want to know how much work he's done up to here, so how much work has the ant accomplished having pushed the seed to here? How would we represent that? Samantha wants W of 0, 2. I tried to make it a 2. I did my best to make it a 2. So she guessed correctly, right? So I was trying to make it about 2. Right, and so then W02, it represents that amount of accomplished work by the ant pushing the seed up until that point. And we could, right, so in GC, so we won't take the time to do it, but in GC we could put this rate function in, define this rate function, define this work function, and then all we have to do in the next line is type that. And the number will pop up. How much, in Newton meters, how much accomplished work the ant has done pushing the seed up to that amount, right? This is all familiar. We've done this all before. Okay, any questions? All right. So now we want, now the ant pushes the seed along the path. The ant pushes with a force of 0.03 s plus 1, where s is the number of meters the ant has traveled so far. So this is kind of maybe like a more realistic way of thinking about it, because it would be, the force would be a function of how far the ant has traveled, not like a function of x. Before it was just a constant. But now the force is changing according to how far the ant has traveled. So the ant is getting stronger, right? So the farther he goes, the more force he pushes with. Okay? So, same question. Same path. But now we have the force as a function of, so we could write this as F, capital F for force, not to be confused with little f for the path, right? Capital F of S equals 0.03 s plus 1. So again, we want to end up with the work function. Work as a function of, we want work as a function of x. We want to write W of, okay? So now we can't just write it down. We got to think of a strategy here. What is going to be our strategy to get here? What are we going to need in order to write work as a function of x? So given that you have the force as a function of s, right? How are you going to get work as a function of x? So in strategy, so we're going to have to figure out what are we going to have to do first here to get towards work as a function of x. Who figured something out here? Volunteer. Yeah. So you want, are you talking about here? So what you're trying to get is, instead of, you still want a force function, but force as force function of x. And if we want force as a function of x, we need, what does that mean we need? We need s as a function of x. Is that where we're going with that? So the question is, what is s as a function of x? Meaning, how far has the ant traveled as a function of x? What's that? Arc length. This is exactly the arc length function, right? This is exactly the arc length function. And how do we write the arc length function? Is it the square? Is it the square root? What is s of x? Just the square root? What's that? Yeah, so this is our integral from 0 to x of square root of 1 plus f prime squared dx dt. So in order to get the force function in a way that we can now use it for work, right? We need that force function as a function of x, and that means getting s as a function of x. So we've got this like composition of functions going on, right? First we have to define this. First we have to define s of x, right? That allows us to define f in terms of x, which then allows us, f in terms of x, which then we can write w in terms of x. So there's kind of this process of functions. So let's do this in GC. So we want it so we can see everything clearly and actually get some results here. Let's do this in GC. So what do we have first? Let's write our f as a function of s. Is it big enough to see in the back? Can you read that? I'll just make it bigger. No response. Okay, so there's f as a function of s. But we also need what? S as a function of x. And let's do that with a two argument notation, right? Two arguments there. So what is s of ax? Integral from a to x of square root 1 plus. So we got to define little f too, right? So I want to do f of t. We're going to square that. T. Yeah, but before that, we need what? F of x. I'm not really watching what I'm doing here. Did it work? Does it match? Is it the same thing? Okay, so I got the force as a function of s, and then I got f of x, which is the path. So now we got the arc length function for s. But really now, what is this f? So let's see. Right, okay. And so then, are we ready to write the work function? No, ready to change? Or what? Who said no? Why not? Big F of x. Big F of x. Okay, what's that? Okay, but isn't it? Well, so we actually don't need to. We've defined the function f and the function s, so we don't need to redefine f here. We can just when we need f, we're going to use not f of s, but we'll actually use our functions in combination, in composition, when we need it. So I think we're ready to write the rate function, right? So what's the rate function going to be? So what is our rate going to be? Remember last time we had it as just simply 0.03 times that so this was our rate, right? Our rate was the 0.03 and so what will it be now? So instead of the 0.03, we have what? big F, right? So but it's going to be big F of this function, right? This function, little s of zero comma x, right? See that? Yeah, no, so I'm not done yet. That's just the force. So that's just, in the last example, that would just be this much. But then we also need this, right? So then we're also going to have times square root 1 plus, this, it's basically this thing again, right? What's that? Oh, no, this is the rate function, so it's still x. This is an integral, right? This is just the rate function, so this is still x. Okay, so force times the square root, that gives us our rate function, just like it did before, right? The 0.03 times the square root was that rate. And so now we're ready to write the work function. What's that? Right, because this was our ds. This whole thing was ds. So it was 1 plus the derivative of the function squared. Remember that? Yeah, so it's the same thing we had before in the first. So this is all the same thing we had before the first time because it's the same path. The only difference now in our rate function is that our force is variable, and now we took our force as a function of s, and we're plugging in s as a function of x, which is our arc length. Okay, so now we're ready to write the work function. We've done that. We've done the hard part, so now we got the easy part. So our work is going to be from 0 to x of integral 0 to x of r sub w. Now is when the t comes in, right? And so what's the work the ant does having made it to x equals 2? .645 Newton meters. Why is it so small? Well, because the force in newtons is 0.03 is really that's 3/100ths of a newton. And so the force up till now is just some factor of 0.03. So that's why that's just a little bit of work, 0.645. And so Newton meters is also, there's a short for that, joules. So this is Newton meters or joules, capital J. And we can easily graph that. We know how to graph y equals getting anything? Oh, it's taking a long time. Why is it taking a long time? Open form, right? Right? So this is this whole idea of we're using open form for all this. We use open form for the arc length, and then that arc length we're plugging it into this function to get the rate of change, and then we take that rate of change and we're defining that the work in terms of the open form rate of change. So is it showing up?
Oh yeah, that's what. Sorry, just a mark on the screen.
There we go. Good. So again, this is the idea of open form functions. When you're the GC is actually calculating this in the spirit of integral because it's having to calculate little bits and accumulate the little bits, right? And so then here is the work function for the ant. So I want you to interpret 3, 1.334 is a point on that graph. So what does that point mean? 3, 1.334. Go. So tell the person next to you, what does that point mean? Alexis. Where's Alexis? What's the meaning of the point? 3, 1.334. Okay, so let's see here. Javier, she said that when the arc length is 3, the corresponding work that the ant does is 1.334. Do you agree with that?
I was thinking meters.
What's that?
I was thinking in meters. Not
What's in me? Which one's in meters?
the distance the ant has traveled up to 3 meters. The amount of work done is 1.3.
Okay, so when the ant has traveled 3 meters, the amount of work that the ant has done is 1.334. Agree? It's not right. Distance from the starting point. Yeah, Bryce. Yeah, remember, what is the 3? The 3 is the x-coordinate. The x-coordinate of the ant. So, yeah, so when the ant has traveled to the place where now the ant's x-coordinate is 3, because this was all a function of x. We ended up with work as a function of x. Then, is it the work currently being done? Accumulated work. All the work, accomplished work up to that time. Okay, any questions? Yeah?
If there was some work accumulated like before 0, then we would say like work of 0 to x minus work of 0 to 0.
Wait, say it again now?
So like if some work was like accumulated before
X
equals 0.
Okay.
So we would say w of 0 to comma x is equal to w of 0 comma 0 plus then like.
Well, we're interpreting the meaning of this. Ask me after class. I'm not sure what your question is. I'm still not getting your question. Okay, any questions? Yeah, Maxim.
What's the difference? Like, why are we saying that like x equals 3 instead of just like when it travels?
Because there was a difference between s and x, and we went through all those functions, right? So originally the force was a function of s, but our f is a function of x. And remember, we said we need to get, if we want the work as a function of x, we need to get arc length as a function of x and plug it into this force function so that the force was a function of x. And so then everything after that was all as a function of x. This was originally we were giving the force as a function of the distance that the ant traveled. But then all this stuff that we did was to make our independent variable x instead of s, because that's just consistent with our with the function that he walks on. So does that answer it? Because everything, so yeah, f was a function of s, but our strategy was we need to get that force as a function of x. So that meant getting s as a function of x, and that was. And so then here we plugged in that s as a function of x into f to get, this is now the force as a function of x. And this was our arc length as a function of x. So this is our rate as a function of x. So then everything from there on was all a function of x. Yeah? So here, this is not accumulation. This is the rate, the arc length. Oh, yeah, you're right. I'm not sure why it worked. Do we get the same thing? That's the question. Looks like it's the same. But you're right. Yeah, we should have had a DT there. So either we got lucky or we were wrong. Let's see. So, did you have a good weekend? Is it looking the same? So, occasionally, GC does read your mind when you put something in wrong, but usually it doesn't. So maybe somehow it's 3. Oh no, it's not right. Oh no, 1.324. Let's see. Yeah, it looks the same. Yeah, that point is the same. Yeah, it's the same. But he's right. We need a DT there. We need a DT there.